Okay, so we're going to do the endocrine system, first of the two chapters that we're going to be doing in this, for this unit. Just to get us to kind of reconnect with where we were with 201, the nervous system versus endocrine system. 201 is all about the nervous system, and now we're adding the endocrine system. So the nervous system, I like to think of it as being the hardwired, like a landline phone, where it has to have a physical connection to where it's going. You know, so it's got to go to the brain, straight to a muscle, and then it's got to go straight to there. Where the endocrine system is it releases a bunch of chemicals. So the nervous system has chemicals that are neurotransmitter. Endocrine system has chemicals, and they're called hormones only because they're in the blood. That's the critical difference, is you have some gland somewhere, dumps these chemicals into the blood, and now it's traveling throughout the whole body. The trick is where there is a chemical, there must then be a receptor for that chemical to fit into. So some hormones are going to have receptors everywhere, all over the body. Estrogen, testosterone are two types of hormones that have receptors all over the body. Then there's some hormones that we'll learn about that are called tropic hormones. That means like targeted. It means although the hormone's traveling all over the whole body, exposed to all of the cells, there's only a specific location that the receptors are. So it only has an action in some places. So it can vary. But the time frame for hormones can be minutes to hours. They take a long time. One example that you guys should have learned about in 201 is when we did the autonomic nervous system. If you get, you know, all of a sudden maybe you're watching a movie and, you know, there's a suspenseful part, and then all of a sudden someone jumps up behind you, like your little brother jumps up behind you and scares you, and it scares the beans out of you, and you jump up and your heart's racing. So that immediate response to being frightened would be the nervous system side. That was your autonomic nervous system, the sympathetic pathway, going to, you know, like telling your stomach, let's digest later, telling your pupils, open up, look for danger, dilate blood vessels to your muscles so we can run away. All of those things are instantaneous, and then you look around and you're like, oh, there's my little brother. Okay, I'm safe, there's no danger, my life is good. But you're sitting there, and all of a sudden your heart rate is still continuing for like another 20 minutes or half an hour. That's because during the autonomic nervous system, if you guys recall the adrenal medulla part, which it not only you have the direct hardwire to your heart to raise your heart rate, but when it went to the adrenal medulla, it dumped out norepinephrine and epinephrine, and now it's circulating. Now it's in hormone style, and that's also targeting the heart. So it ends up being the same chemical onto the heart, but now this one just takes a lot longer to clear. So that gives you an example of sort of the time frame between one. One's going to be more instantaneous, the other one's going to take a higher duration. So we're going to be dealing obviously with the endocrine system, because that's our system now. The difference between the endocrine gland and an exocrine. You guys did exocrine glands in 201 when you're doing these like tissues and skin. You have the sebaceous gland, you have the sudoriferous glands, things like that. Any gland that's an exocrine secretes it out a duct and into a space, where endocrine gland secretes it out the gland and into the blood. So the critical element is one is blood, the other one is going to go out to a space. So I'd like to expand your definition of out to a space or outside. So I like to use the anywhere a penny can go kind of analogy. So if you take a penny and you're rubbing it on the surface of your skin, that means you have sweat glands that come out. Those are all exocrine. Then maybe you take that penny and you pop it in your mouth. Well, that's still considered outside. So there's salivary glands. Those are exocrine. That's making saliva. Then you swallow the penny and it goes down your esophagus and into your stomach. Well, then the stomach is going to secrete gastric juices and things like that. That's still outside, so they're exocrine. And then that penny continues on because your body has not absorbed it into the body. So even though following our digestive tract, it's still considered outside. Our body has yet to decide to absorb it. So that's really kind of the delineation. So once it goes to the stomach, it goes to the intestines, and it goes right out the other side, and look, it's still a penny. So all of those things, those would be exocrine glands that would be contributing juices all along. So that's just to highlight the difference between an exocrine gland that's going out a duct into a space. So you can kind of expand your definition of space, if you will. And then endocrine is just into the blood. So we're just dealing with that side. So here's just an easy schematic. Here's a gland up here. it dumps out these weird little car-shaped hormones. Each hormone is going to have its own little structure and piece because they go to bind to a receptor somewhere. So the receptor will fit the receptor will fit that hormone, and that's how it works. So it's really like a lock and key. So you can, and also not only is it a hormone fitting into its receptor, but where that hormone fits into, it might do different things. So if it's estrogen, you could have an estrogen receptor on your breast, and estrogen can bind to it there and cause one action. You can have an estrogen receptor in your brain or elsewhere, and it could have another. It may turn on activity or it may turn off activity. So it's often tissue dependent. But you have a receptor that fits estrogen. That's also why people, for instance, say like soy or some of those soy molecules are target estrogen receptors for whatever paper you're reading. It could be a very good thing, could be a very bad thing, or the drugs like tamoxifen, those are also estrogen receptor binders. All it is saying is, hey, you have a receptor, whether it's some component of soy, hey, there's a part of soy that kind of fits in there. So in some cases, is it going to activate it, deactivate it? Those, again, may or may not be consistent, which is why soy has such inconsistent data on it. Sometimes good, sometimes bad. But on the other hand, that's the bread and butter of pharmaceuticals, is they're usually affecting the receptor. So for our purposes here, we're just going to talk about, here's a gland, it makes hormones, and it goes to a place. So you're going to need to know the gland, what does it produce, and what does it do? And that's going to be it's going to be pretty linear. So this chapter, there's a lot to know, but at least the pattern is going to be pretty consistent. So it's just a matter of managing it, being organized. So this is kind of from my old school textbook. I kind of put these pictures on end so they would match. So I'm going to go through a series here where we're going to talk about these hormones and their two basic classifications. One is a water-soluble hormone and the other is lipid, so obviously fat or water. Blood is mostly water. So the water-soluble floats through the blood quite easily. Lipid-soluble usually has to have a carrier protein to bring it through. So water-soluble, it has to bind to the cell differently. So this here is a picture of a portion of a cell. So what is this part here of the picture? What is it depicting? Membrane. Yeah, so cell membrane, and what are they made of? Lipid bilayer, excellent. So the lipid bilayers, these two little guys here, so the cell membrane is basically fat. The little polar side here helps it to sort of hang out in the water, but the interior is going to be fat. So if this yellow guy here is a water-soluble hormone, it doesn't go through fat. It just bounces right out. So it's never going to get into the cell. And we don't need it to. So what it does is it binds to its receptors. So in this case, the receptors are orange. So the yellow, say the hormone is insulin. It binds to the receptor on the surface of the cell. And it sort of is like pushing a doorbell where the door never opens. It's sort of like, hello cell, I'm here and you need to do your job. So it never goes in the cell. It basically sits in there and sends a signal. And all this stuff, this mumbo jumbo stuff here, is known as the second messenger system. So if you have a textbook, there's a lot of information and it's really, really important. But I don't have a test question on it. So telling you it's important, but I also don't want you to spend extra time on it unless you really find it interesting. So the second messengers, you'll hear the term cyclic AMP, you'll hear the term cyclic GMP. They are really important things that you will need to know when you get into nursing, but I'd rather you get this big picture concept because the details of what they do can vary and I don't want you to get caught in the weeds. So the point is here, a water soluble says, hey, I'm hitting the surface, I'm going to make all the second messenger stuff happen, and what's the result? This little purple thing is supposed to say, whatever protein or whatever that cell is supposed to do, it just chunks it out. So if this happens to be a thyroid gland, you're going to get a hormone like thyroid stimulating hormone that hits here, and out pops T3, T4. It's like pre-made, and it just says, hey, lettuce and that. It's sort of like a fast food restaurant. You just show up, and you're like, I want some fries. Here you go. Had it ready for you. You know, so it's just instant. But the second messenger kind of had it, was a signal where the hormone never entered. So where lipid soluble, we can see that because the cell membrane is fat, it's lipid soluble, so it travels right to the wall, just like a ghost to the wall. But it ultimately still binds to a receptor, but inside the cell. Now this receptor combination will go to the nucleus here, and in the nucleus, it will then, this sort of depicts DNA, and this will then cause it to say, do the whole transcription and all that stuff, make it in the ER and all that, to then form whatever protein it's going to make. But it really did it on an as-needed basis, so it's more of like a custom job. So it's a slower response because it takes longer to go to the recipe or the nucleus, have it made, and have it output that way. So lipid-soluble hormone activity has a longer time course, and it must utilize the nucleus in terms of that. So I like to explain to you guys like in a big picture so you sort of get it, and then now we'll go through the words. So on this side here, water-soluble, we now know that the receptors are on the membrane, on the surface, so the hormone never enters the cell. It uses the second messenger system, and so you don't need to know the specifics of the second messenger, just that it is. It's going to activate pre-made proteins. So those are already made. It's meant, the cells are sitting there waiting just for the signal to let it go. So therefore, because it has pre-made, it's going to be faster acting. We're going to deal with the examples, but the main thing you should know is that they are protein-based. So this is going to be a big difference because the other one's going to be fat-based. That's what lipid is. So we're going to come back to this. So we're going to rewind this here a little bit. Okay, so for the lipid-soluble side, there still is a receptor. It just is a receptor in the cell. So the hormone itself goes right into the cell. It has a direct action, and the key here is it's a synthesis of new proteins. Therefore, it's going to be slower acting. And the main thing, it's going to be fat-based molecules. So I'm going to show you what some of the differences between these two types of hormones. So this here is just a summary page of just showing you on the surface, instant output. This crosses the membrane, uses the nucleus, and kind of gives you some details here. So this is a bit of a summary for your review. So instead of memorizing this list of like, oh my goodness, I have this whole list of which one's water-soluble, which one's lipid-soluble, just don't worry about this. I'm going to tell you an easy way once I go through my little speech here of how to memorize them. So just know the main thing is water-solubles, surface, second messenger system, pre-made, faster acting. Water-soluble is protein-based. They look like this happens to be growth hormone. And so each one of these dots is an amino acid. So each amino acid, when they're linked together, like basically it's sort of like really high-tech Legos where you like link one to the other, but if it happens to be like a red one with a green one, it's going to have to go at this angle. Like one amino acid linked to the next amino acid determines the angle that that protein goes to, which is why protein building blocks can make something like hemoglobin or hair or muscle cells, or so they have different things based on the order of these sequences. So anyways, what you have is basically all these beads, and it makes some sort of formation. That formation is going to ultimately what fits in a receptor. But they're protein-based. They can go through the blood quite easily. They don't need to carry a protein. Where lipid-solubles, I'm going to give you this chicken wire diagram. So this is the classic chicken wire diagram from a chemistry class. So no chemistry here. There's a few things in chemistry that we're going to dabble into. But what I want you to see, and I erased all the names, but I want you to see, obviously, what's common amongst these hormones. So on this page, you will see pregnenolone, you'll see DHEA, you'll see all three versions of the estrogens, you'll see testosterone, you'll see aldosterone, you'll see progesterone. So all of those things, there are quite a number of different hormones I just named, but they all have the same basic backbone. And these rings here are the basis of what cholesterol is. So you can see here. So this is actually what cholesterol looks like. We use cholesterol to make all of our sex hormones, as well as other steroid-type hormones. So when we say steroid hormones, I'm not meaning in the gym, pump me up, giant person, get humongous, because that's sort of like the definition of steroid that goes to mind. Steroid hormones really means anything that's on this chicken wire diagram. They're all steroid hormones. So what they are is they're cholesterol-based. But one thing that I just like you to appreciate about these here is we look at testosterone and estradiol, which is what the main estrogen. Look at those two, and you can see that there's very, very little difference. Like basically, we just have a double bond to this O compared to here, and then another change here in the hydrogen. Pretty minimal. I mean, super minimal chemistry between estrogen and testosterone, but huge difference in a person. You give a man a bunch of estrogen and he's going to be buying a bra soon. You give a woman a whole bunch of testosterone and she's going to be shaving pretty quick. I mean, so it has really profound body impacts on just pretty minimal things here. So, but they all are related. So one thing to think of is oftentimes cortisol we see on here. We're going to learn on Wednesday that cortisol is our main stress hormone. So what happens when people are super stressed out? You're going to get a lot more cortisol and a lot less of this. So many, because when you have a big diagram like this, is if you're all of a sudden making more through this pathway of this, then that means you're going to be making less of that, because it's all unbalanced. So often, that is how stress has an impact on our whole body, because you raise one, but therefore you only have enough cholesterol to make a certain amount, so you lower the others. So I wanted you to have that big picture view and appreciation of this. So now we'll come back to the topic specifically at hand, which of the lipid-soluble hormones, instead of memorizing this whole list, think of them mostly as our sex hormones. And not all of them are, but you can see them right here. So testosterone, everyone's pretty familiar with testosterone, and estrogen, and progesterone. Some of the others are probably less familiar, mineral corticoids like aldosterone, the glucocorticoids like cortisol. They also are in that big chicken wire diagram, so therefore the lipid-soluble family. So, but the point I want to make is I want you to appreciate that there's sex hormones are related to all these other hormones, so that you can vary in them, and that could be the basis for some pathology. Someone could be estrogen deficient because they're cortisol excessive. So sometimes where you're deficient in one, you're excessive in another. So know that from a health perspective. But for this class, specific for your test, and what I need you to know from here's going through our notes, what's important is water soluble, lipid soluble. Water soluble, we know hits the surface, second messenger system, instant pre-made comes out. Lipid soluble actually enters the cell, goes to the nucleus, makes brand new proteins, takes a little longer. So, and of the group, sex hormones are going to be in the lipid soluble. So on your exam, instead of coming up with some sort of weird name over here, like one of the thromboxanes, I'll just say, estrogen has a receptor where? A, on the surface, B, inside the cell. So that you'll know estrogen or testosterone or progesterone would be the hormone of choice for the lipid soluble. But just know it's a family, and that I want you to have the appreciation that there are other hormones that do indeed do that. But my point here isn't that you have them all memorized, but I want you to know how they work. So if I want to know about lipid solubles, I will use one of these as your example. And then there's which of the following hormones would, affect the nucleus of the cell? And I might say insulin and thyroid stimulating hormone and testosterone. And so you're like, okay, it's not one of these. And so instead of memorizing insulin on the water list, just know what's on the sex hormone must be water. So you can just kind of memorize these little ones. I care more that you understand the mechanism and use these as an example. Okay. So here's more pictures showing the second messenger system here. This is that without. Here's a lipid soluble where you have the blood coming across the membrane, going here through the DNA, going through the ribosomes, and making your new proteins. So lipid-soluble hormones can also have a greater impact. That's why some of them can be more associated with cancers too, because they're having an impact in the nucleus and the DNA too. So that is the summary there. So for this section, nervous versus endocrine, one is direct nerve connection, the other one's via the blood. Endocrine versus exocrine, again, blood versus going out a duct into a space. The classifications, water soluble versus lipid soluble. So you've got the sex hormone in one, or all the others in the other. And then, how do they work? One's on the surface, one crosses the membrane. One sends out pre-made protein, the other one has to make fresh proteins each time. So that's pretty much what I need to know from this section. So the hypothalamus, pituitary. The hypothalamus, you guys should remember from 201 where it was, right in the brain. Feeling good about that? So it's right there, part of the diencephalon. And so it's in this sort of central part of the brain. We have the hypothalamus is kind of an old slide here, but I wasn't sure how to change it. Conceptually, I'd like you to think of the hypothalamus here up in this portion of the brain as a receiver of information about your body. Like it's constantly like the Pentagon. It knows like what's going on all over the world. It gets satellite information, and knows what's going on in space, and knows what's going on in Russia, and knows what's going on in like Antarctica. You like knows what the New Zealanders are up to. Like, you know, there's spots, whatever it is. So it's basically a place that gets information, a lot of different information about a lot of different things.
It's like the control stuff.
But think of it as more receiving initially. So right now it's more about like, in order to exert control, you have to have information. So the hypothalamus is our biggest reception of information on the body status. Are you hungry? Are you hot? Are you cold? Are you nervous? Do you have a high concentration of solutes? Do you, are you aroused? Are you lactating? Are you like, there's all kinds of information that it's bringing into your body, into your brain. And therefore, based on the information coming in, it then can say, I'm going to have an action out to the body. The hypothalamus receives all of this information. And who's the workers that get it done? The pituitary gland. So the pituitary gland are going to be actually what's getting presented throughout the whole entire body. So one thing to consider, hypothalamic hormones, you're not going to do a blood test. You're not going to take someone's blood test and go, hey, how's your hypothalamus doing? You're not going to know about it. Basically, you only know because it tells the pituitary to do something, and then that's what's going out throughout the body. So I want you to have that sort of sense of disconnect. So although it's a master controller, it's really not the one doing, it's a puppet master, but it's not the one that's actually circulating through the body, actually hitting those receptors and having the action.
It delegates.
So, yes, master delegator. There you go. That's it. Receives all information and the master delegator throughout the body. So the pituitary gland and the 8 hormones are going to run from there is going to be the workers. So that's why I wanted to have that hierarchy. So here we have information to the hypothalamus as it's receiving it from the body. Oops. And then it receives it from the body, but the action is via the pituitary gland. So, and then it's the pituitary gland that controls the body. So that's really what I wanted, the concept I wanted you to have in place. So now that we've got that hierarchy established, I want you to now we're going to figure out how it happens. So the hypothalamus is a zoomed in view of the diencephalon. Hypothalamus is sort of this section here, as it's sort of like a duck beak, if you want to think of it that way. And then the pituitary gland sits below it. Who remembers from your 201 class, being the skeletal system, where the pituitary gland sits? What brain structure, what skull structure did you find location of the pituitary gland? Okay. It's also, so hint is Turkish saddle. That made it worse, because like my 2 other classes were like, what? Now that's even like more nutty. There is a spot in here known as the Turkish saddle. The term you should have learned of is called sella turcica. Does that ring any bells? Okay. You're with me on the sella turcica. Okay, so the sella turcica, so if we're here with the skull, with the face, looking straight down, the sella turcica is right here. Put a sticker here. So what it is there's a back part, or else you can see so well, where it's scooped up. So it's a saddle, so I call it the Turkish saddle. And in fact, if you look at it from this angle, you can see the 2 optic foramen, where the nerves are coming in from the eye. And you probably knew already about the optic chiasma, the X, that those 2 optic nerves make. So basically how this is positioned, how the pituitary gland, it actually sits down in here. So what I'm teaching the 201 class, so we do it very often in person, is if you imagine a tiny little Barbie doll, like shrunk down, Barbie tiny, and she's sitting in this Turkish saddle, facing forward. So you imagine the Barbie doll sitting in her saddle, and then her arms are just projected straight forward. They will be going through the 2 optic foramen. So in that position, Barbie's butt is the pituitary gland. It's just going to sit there in the saddle. And therefore, kind of the level where her arms are, that's where that optic chiasma is, where then below is where the space of the pituitary gland. So I only tell you this because one, I'm trying to make connections back to 201 whenever I can. Two, is to kind of let you kind of visualize that, because when we dissect brains here, most of the time when you take the brain out, the sheep brains that we usually dissect, the pituitary gland almost gets stuck in there, so it gets pulled off. So you rarely dissect the pituitary gland in the brain. Sometimes we buy them where you actually chunks out pieces of the bone with it for that purpose, but we rarely do that. So I wanted you to know that. The other is people that have a tumor on their pituitary gland, and we're going to learn about all these hormones the pituitary gland secretes. Often, one of the earliest symptoms is actually vision changes because it's encroaching on that optic chiasma. And so even though the effect of a tumor on the pituitary gland may have nothing to do with, whatever the tumor is doing, it just physically is in that proximity. And the other thing is on a pituitary gland is because there's all this brain tissue around here, if you're going to do surgery on it, you're not going to come pummel through here. You're going to actually go up through the nose. And that's going to be the most effective way at having access to it. So I just bring this up. Remember that, and know that when we give you these random weird terms like celitarsica, that actually has some point at some, maybe. So here we go. So we're the hypothalamus, pituitary gland. How it talks with the pituitary gland is through this little stalk or connector called the infundibulum. So the pituitary gland, even though we're talking about hypothalamus, but the pituitary itself is made of two different parts. And because it's two different parts, the hypothalamus has to talk to it two different ways. So that's what we're going to talk about now. So this is kind of a little crossover. The anterior pituitary, or the front part, is connected by hormones. That's how it has to get a hold of it. Because it's not physically, but it can only send its signal. So it's sort of like the anterior pituitary, the hypothalamus says, hey, I really like that anterior pituitary to send out growth hormone. The hormone that we haven't done yet, but it's coming up, and it's going to be the anterior pituitary. So if the hypothalamus says it's time for us to grow, and I need to send that out, it literally says, I'm going to send out growth hormone, releasing hormone. So it's like a little letter it puts in the mail, in the blood, that's going to go from the hypothalamus down here to the anterior pituitary. It looks at the letter and goes, I'm going to send out growth hormone. And then it sends it out to the whole body. And then when it wants to stop, the hypothalamus sends out into the blood growth hormone, inhibiting hormone. And then this one says, okay, I'm done. No more sending out. So it's sort of just like a weird little message system, but it's only through the blood. The posterior pituitary is from the hypothalamus. There's actually a direct nerve connection, so it's a lot more efficient. So it's just weird, but there's just two different ways that they control each other. And so we'll go through this a couple of different times in a couple of different ways. So here we have the anterior, controlled by hormones. The posterior is going to be controlled by nerves. So here is my awful photoshopped version of the anterior pituitary connection. So basically you have a capillary system here in the hypothalamus, and it sends out some sort of signal or releasing or inhibiting hormone that goes to the anterior pituitary, so I'll shrink that down here, to the anterior to tell it to send out whichever one of its many little minions it wants to send out, and therefore the inhibiting hormones. And then the posterior is more of a direct, again, nerve connection. So the portal system. So I wanted to mention what a portal system is as far as terminology, because you'll see this in reference to on a test. So what the hypophyseal portal system, the hypophysis means pituitary gland. So hypophyseal portal system is referring to the blood vessel, the two capillary bed vessel. So for instance, a normal situation is the heart sends out oxygenated blood out to, say, the kidney. Goes to the kidney gets its oxygen, gets what it needs, then sends it out the vein, and it comes back to the heart. Goes, so we'll learn about that next week. But you basically go from the heart out to a capillary bed in some place and come straight back through the vein and go back to the heart again. And through the system. Unless it's a portal system. Then it goes into a capillary bed up here. Here comes from the heart, heads to a capillary bed, and then it goes to another capillary bed, and then it goes to the heart. So all it means, there's only two in the whole body that it does that. One is here in the brain, hypophyseal portal system. The other, I'll just tell you about it, but I don't care that you know about it yet, but you will need to know about it in Unit 3, is called the hepatic portal system. So essentially the heart sends blood to the guts, who ate some lunch, and so your guts are absorbing the nutrients from your food, and so instead of taking that straight through the veins right back to the heart again, whatever you just recently ate, your body's like, you know what, you might have brought in something that we don't really want circulating. So it goes from the capillary bed of the intestines to the liver first, to check out and pull out anything that we don't want, and then back to the veins and back to the heart. So again, it just means two capillary beds, that's all. So I wanted to clarify that terminology. So this slide is really just about, I'm going to say conceptually, it's the whole releasing hormone and inhibiting hormone. So if we have, say I'll draw this hypothalamus, and then we have our infundibulum, and then we have our pituitary gland. And so we're going to deal with our anterior pituitary. Another color. So let's do green. So what the hypothalamus does, if it's going to have to go through the portal system, because it's going to the anterior pituitary, which means it's got to tell the pituitary, because we have 6 hormones that come out of here, which I'm jumping ahead, but just to let you, so one of them is going to be growth hormone. I'll just do another one as being prolactin. So those are 2 that are from the anterior pituitary. So say we'll use prolactin as an example. So if, let's say, a lactating female, the hypothalamus gets the signal that new breast tissue or new milk needs to get made because you gotta go nurse the baby. So what the hypothalamus does, it's going to send down here prolactin. Put this in caps. Releasing hormone. So that comes on down to the anterior pituitary, and then it knows, hey, okay, I'm going to send this out. And that goes to the breast, starts making milk. So that's why it's called prolactin, means prolactation. Breasts get full, feedback comes back here and says, we got enough. And so then what it does is it's going to send out prolactin inhibiting hormone. It tells it to the anterior pituitary, and it's like, you know what, we're done. We don't need to anymore. So I'm going to go through this set of slides here that just kind of goes to walk you through your notes. But really, what I care about is that it sends out releasing or inhibiting. What I'm trying to say is, no matter what the name of the hormone that's coming from the anterior pituitary, if you see the word releasing or inhibiting, it means it's from the hypothalamus. And it's super simple now, but it's something that more than half the students get wrong on the questions on the test, where I would ask, growth hormone, releasing hormone comes from which location? And by the fact that it said releasing hormone, you should be like, oh, automatic, hypothalamus. But we get so caught up in the next section of the pituitary gland that you're like, oh, growth hormone. And that's all the students will see. And they kind of miss the trigger word of releasing or inhibiting. So I want to bring that to your attention. Small detail that often gets overlooked in the studying, but is an important distinction. So again, there's a couple questions like that. So here's the sequence. The hypothalamus will send out a set of releasing hormones. So it could be any of these, but it has the word releasing in it. We know it came from the hypothalamus. And that's going to activate the pituitary gland to send that hormone out. Then we have a series of inhibiting hormones, again, that would stop the release of that hormone from going out. So again, anything with this word inhibiting in it, prolactin inhibiting factors or hormone, it depends on which book you're looking at, so you change some of the names slightly, but you can sort of see growth hormone. Thyrotropin would be for thyroid stimulating hormone. We'll get to that, but that if it just has the word inhibiting or releasing, it came from the hypothalamus and it's going to the anterior pituitary. But you will not see it throughout the body. You're not going to pull a blood test and be able to see it because it's going to be stuck only in that little capillary network. Okay. Then the other side is the neural connection is we have these nerves. The hypothalamus says, hey, I've got 2 hormones in the backside that I'm going to release out, and that's pretty easy. It just stimulates it and it dumps into the blood and off it goes. So the posterior pituitary is super simple. And it only has 2 hormones, so it's double. So here's our summary for the hypothalamus before I jump into the pituitary gland, and then before I listen to that talk. Diencephalon, that's the part of the brain. It gets all this information in. It's an information receiver. And then it's going to control the body through the actions of the pituitary gland. So as she pointed out, it's a delegator. So it tells the pituitary gland to do it. And so it does it by either sending out inhibiting or releasing hormones or a direct connection to the posterior side. Is that pretty good? Feel pretty confident? Okay. So I'll go through, I'm going to go through the pituitary gland quickly just because I know a lot of information on you and it's kind of a lot of sitting here. But I did want to kind of get into the content so that when we come back on Wednesday, we can just kind of recap this and then move on. And that way you have kind of enough to go through. So I'm sort of like, stuff in the suitcase here, full of little extra information. Sorry about that. So here's a cross-section piece so you can actually see the pituitary gland. This would be the nasal cavity. So you can see if you're going to do surgery, like you bust through these sinuses here, and there's the pituitary gland itself. That white thing is actually the middle of that optic chiasm. So you can see that position here. Okay, so the pituitary gland is known as the hypophysis. That's the hypophyseal flow system. The posterior pituitary, so you'll see that there's a couple layering. Like I'll kind of repeat stuff because now it's from the perspective of the pituitary. So sometimes there'll be things that are just repeated, but it's from a different perspective and it's sort of like layering the information on. So the posterior pituitary, we call it the neurohypophysis. So hypophysis means pituitary. This one's obviously the one that's controlled by nerves. Where the anterior pituitary is called the adenohypophysis, and we control it by the hormones. And again, we talked about the inhibiting or releasing hormones. So what does it look like? So from now on, for each gland that we go through, we're going to see a histology picture of it. So on Wednesday, we're going to try to get through the rest of the information and have time to look at slide images and have the lab activities. So the pituitary one's the easiest one. So here you go. You got 2 sides. It's like a circle and it's 2 halves, kind of. Our slides here aren't as good as this. So this is usually the one I use on the test, actually. So this looks like this, and so you have the anterior pituitary, also known as the adenohypophysis. We're going to learn about 6 hormones. It actually releases 7, but we'll learn about 6. And then we have the posterior pituitary, where it has 2 hormones from this side, and it's the neural. And when you're looking at them histologically, the neural side is really plain. It only has 2. So the other side is more chunky looking because it's making more hormone. So we're going to go through the 6. And we'll just kind of go through them quickly. And then I have a summary slide at the end that sort of just, we can kind of put all of this together. So antidiuretic hormone is the first one. Just even looking at the name, who can tell me what you think it does? Yeah, it's like, think of it, don't pee. The don't pee hormone, like antidiuretic. So it basically says, you know what, you're not drinking a lot of water, and we're really kind of concentrated with our electrolytes. So maybe we shouldn't let so much out. Let's keep some more water in our body because we need to maybe be less concentrated. And since you're not drinking any, we need to conserve it. So that's basically what it's doing. So when antidiuretic hormone gets sent out to the body, it's telling the kidneys, you know what, don't let so much water out. So that's what this is, so more retention, less excretion. And it also increases blood volume. But we're going to deal with the blood volume story when we get into the blood vessels. So antidiuretic hormone is something that we're going to see in 3 of our 4 units. Now, in the endocrine system, in unit 2, because it's part of blood pressure, and in unit 4, because it's part of kidneys. So we'll actually see it a couple there. So oxytocin, that's the next hormone on our list for the anterior pituitary. That one is going to target uterine or smooth muscles. Most people are familiar with oxytocin for going into labor. It induces labor. So someone's having a baby and it's not coming, and they start giving them an oxytocin drip. What that does is it targets the smooth muscle of the uterus and causes it to contract and push out whoever's in there. Let's get out. So that's its job. So in general, it's a smooth muscle contractor. So what else it does, it also is involved in milk ejection. So the example I gave you here is prolactin, which we'll get to in a little bit. Prolactin means prolactation. So it's targeting the glands and make the milk. Oxytocin is surrounding the ducts and it delivers the milk. So that's again, that's another smooth muscle action. So in men also has oxytocin. They just don't have some of these benchmark or hallmark body functions like nursing and giving birth that women do, so they don't have as much opportunity in that way to use them in the volume that we have. But men also have every single one of the hormones that we talk about. So I want people to, although we focus on the female activity of many of these hormones, this one and prolactin, men do indeed still have that hormone available to them. They obviously don't release it. Oxytocin, though, they probably utilize it too. Oxytocin, not only smooth muscle, it also is involved in orgasm. It also is involved in nurturing, both prolactin, more oxytocin. It's known as the hormone of love. Besides the orgasm part, but it also is involved in bonding and things like that. So there are some psychological aspects that they play a role. So we're sort of just dealing with more of the physical type of aspects here, but only because the fixation's on females and the immediate role there, I wanted you to realize men do indeed have these hormones as well. So those are the two posterior pituitaries. So we have, here's my summary slide for the posterior. And from a nerve, from the hypothalamus via nerve, antidiuretic, water retention. Remember, don't pee. Posterior pituitary oxytocin goes to females for milk ejection or uterine contractions. Men, not so much of those, but again, hormonal love kind of story, but we have that. But they have it, so I have that as a list there to just acknowledge that they have it. The anterior pituitary, we'll go through these. Thyroid stimulating. This is the first one that's a hormone that's known as a tropic hormone. It's spelled tropic, but it's pronounced as tropic. You don't see it here. But tropic hormone means even though it's going to be circulating throughout the whole body, from your toes to your guts, through your ears, through your brain, the only receptor in your body for its action to take place is on the thyroid gland. So that means it has a target, a specific target, even though it's circulating everywhere. Something like testosterone and estrogen, they've got receptors on every cell of the body. So it's just everywhere, growth hormone. But this is a tropic hormone, and then it's got a specific target. So this one's called thyroid stimulating hormone. So it goes from the anterior pituitary to the thyroid gland. It will then, and we'll learn on Wednesday, the effects, basically metabolism. We'll deal with T3 and T4 on Wednesday. So the other one, this one is known as Adreno, corticotropic. So you kind of break it up. So it's like the $100 word. So it's a really long, ridiculous word, but it tells you exactly what it's going to do. A, it's a tropic hormone, so it's only going to one place. That place would be the adrenal glands, and specifically the cortex. That's the cortical part, and it will release corticosteroids. So sometimes, even though the names that you guys are going to have to memorize are ridiculously long, sometimes they do help you out, and they tell you kind of what it is indeed doing. So if you kind of think of them, kind of break them up a little bit, that's going to help you. So cortisol is the main one that comes out of here, and we'll talk about the adrenal gland also on Wednesday. So some of these after effects, that's why I'm going through it quickly, is we're going to get into a little more seriously on Wednesday, and will be from stress. Luteinizing, so I have two in a row here that are known as gonadotropins. So gonadotropins, it's plural because I have this one and the next one, luteinizing hormone and follicle stimulating hormone, meaning they're going to target the ovaries or the testes. So they're targeting our gonads. And so they're doing, one's either gonna secrete the hormone, estrogen or testosterone, and the other one's gonna make the gamete, sperm or egg. So that's pretty much what they do. So they're, if one's making sperm in females, or no, sperm in males, to make eggs in females. So luteinizing hormone is the hormone one. It's gonna target the gonads, ovaries or testes, and it's gonna release that hormone. So if it's a female, it'll stimulate estrogen production. If it's a male, it'll stimulate testosterone production. So that would be luteinizing hormone. The other gonadotropin is follicle stimulating hormone. It will also target the gonads, ovaries, and testes, and in the females, it'll make an egg. In males, it'll produce sperm development. And so we go over these two again, we do uniform, we do reproductive system at the end. So here we go. And 5, okay, we're almost done here. Prolactin, you guys already know that one. Pro-lactation, promoting, so it targets the mammary glands, the breast tissue. Increases milk production. So who remembers the hormone that actually caused milk ejection or the delivery of milk? Oxytocin. Oxytocin, perfect. And then we have prolactin that makes the milk, so those two work together. And so the feedback cycle actually, so women that are nursing who actually get into a cycle whether their kids eat every 2 hours or eat 3 or 4 hours, but all of a sudden, if they're like in town, the kid's a babysitter and you're past the 3-hour mark, your breasts are getting pretty big and tingly, and you're like, because it's now on this feedback cycle as far as feedback to the hypothalamus, when to produce and when not. And if then you go longer, then the feedback can be adjusted. So that's usually the, and so we'll talk a little bit about on Wednesday, hope to remember to do that, the whole negative feedback cycle for some of these, so we can kind of get, and so that's why I sort of put these so later. I don't want you to feel like you have to memorize these step by step. I want you to understand what a hormone's doing, and then you can work these through yourself. So if you're like, hey, prolactin makes milk, okay, what would be the negative feedback cycle of it? Okay, you know, breasts are depleted, might be like post-nursing, so the stimulus goes to the hypothalamus, and it's held the anterior pituitary, and then it goes, and then breasts get filled, and it tells the hypothalamus, and sends the inhibiting hormone. So you want to work out the negative feedback cycle. Don't feel like you have to memorize it as a list, then it becomes too overwhelming. So if you understand the concept of how it's going, and you're like, prolactin is making milk one, then you can fill in the between and not be so overwhelmed in your study. So the last of the 6 that we're going to go through here is growth hormone, and it does what it says, blessedly. So it's going to help you to grow. Mostly in children. Children grow mostly at night. So we'll talk about, when we talk about melatonin, how important it is to have dark rooms and the kids to have dark so they can actually have an appropriate amount of melatonin, which actually is a signal to have a growth hormone released, so they grow better in the dark. But I know plenty of big kids that have red lights, so you might don't think you're stunting your kids' growth, but it is supposed to be better and more effective growth hormone release when you have less light available, because it's linked with melatonin. So, and we'll go into some of the other pathologies of growth hormone, but I want to finish with this slide, so I'm not sort of a series, so it's not so instantaneous, but just so we can leave you with this sort of recap of the hypothalamus to the pituitary, and then kind of go through each one of these we just did quickly, and then now you have something to think about, and then we'll kind of start off next time like this. So first one, we're going to do thyroid stimulating hormone. See, I tweaked the name a little bit. So this is actually the name that's in the textbooks. I actually call it thyrotropin, but the key is the release. It's got the release. So it's coming from the hypothalamus. That would be like here. And then here it goes down, coming down infundibulum, goes to anterior pituitary, and from the anterior pituitary, out would go thyroid stimulating hormone. And where's it going? The thyroid gland. And it goes to the thyroid gland, and then on Wednesday, we'll learn about thyroid gland, and we'll learn that it can deal with growth and metabolism. Then the next one, corticotropin releasing hormone. That goes down the infundibulum. That goes the anterior pituitary. Out goes adrenocorticotropic hormone to the adrenal gland, specifically the adrenal cortex. You'll learn those details on Wednesday. You're going to deal with stress. It's kind of in the middle here. Stress hormone, cortisol is the main stress hormone. Then we have the 2 gonadotropins I have together here. They're not released together, so I sort of should have made them independent, but there's luteinizing hormone, That's going to go to the gonads, or you've got follicle stimulating hormone also to the gonads, whether you're dealing with the testes or the ovaries. But they do different things. They're still going to the same place. So the luteinizing one is the one that increases your sex hormone, that'd be testosterone or estrogen, where follicle stimulating is going to be with the sperm and egg development, depending on who you are. Prolactin releasing hormone heads the anterior pituitary, drop it down there, heads out with prolactin, and it's going to increase milk production. And last but not least, growth hormone, again with the releasing. So I still want you to just kind of keep fixating, even though it's like now old news, it's going to feed into you, that hopefully when you get to the test, when I ask you about a releasing hormone, you'll just immediately go, hypothalamus. And then it goes out to the body, goes everywhere, growth and cell division. So call this good. Let you kind of go, okay, so your brain's full. So we'll kind of let you sort through. We'll come back on Wednesday. We'll go through some of this stuff here, and then we'll recap this, and then we'll start on the thyroid and pancreas and adrenal gland.